Hello friend, good morning and welcome back to your favorite technical channel AVM Tech Android. So today I am available with the third video lecture related to heat transfer by means of radiation. This is a QR code of my channel and this is the name of my YouTube channel AVM Tech Android. Either you can search AVM Tech Android on the YouTube and you can take the benefit of free lectures, or you can scan this QR code and you can enter into this channel and you can enjoy free video lectures. So in the present video we are going to discuss about numericals related to heat transfer by means of radiation based on governing laws for heat transfer by means of radiation. So all these figures which you can see were already discussed in the previous videos. The links are available in the description box. You can refer that link, and if you wish you can again recall the laws which are mentioned in the previous two videos. So this is talking about absorptivity, reflectivity, transmittivity. We are discussed about Planck's law, Wein's displacement law, and this is about absorptivity plus reflectivity plus transmittivity, that is equals to 1. So all the theory what we had discussed till this point, based on that numerical will be there. So let's start the numerical part for heat transfer by means of radiation based on governing laws. So the book which I am preferring is Heat Transfer by Dr. A.V. Mehta and Professor P.G. Choksey from Books India publication. So we are discussing the first numerical, that is following data relates to furnace used in the thermal power plant. So these are, you can say, numerical which are there, or the problems which are faced at industry. So whatsoever we are discussing is actually related to industry only. So we are talking about the furnace used in the thermal power plant. Assume the furnace is a black body. The temperature of furnace is 2773 Kelvin, and we have to find out monochromatic emissive power at 1.2 micrometer length, wavelength at which emission is maximum, maximum emissive power, total emissive power, and total emissive power of furnace if it is assumed as a real furnace with emissivity equals to 0.9. So this is the data available with us. Friend, this is a very simple numerical. This kind of question will be asked in the internal test, in the university exam, as well as in the competitive examination. So what we had discussed in the previous videos, according to that you have to remember the constant values which we have to use at present also. So here in the data, first what is mentioned, that is we have to assume the furnace is a black body. So emissivity, that is equals to absorptivity, and that is equals to 1. But in the last question it is mentioned that we have to find out the total emissive power of the furnace if it is assumed as a real surface with the emissivity that is equals to 0.9. So as a black body we have to do some exercise, and then we have to consider that as a real surface, and again we have to find out what is the total emissive power. So these 5 different small questions are there, or 5 different small problems are there, and we have to find out what is the answer. So the furnace temperature is available in the Kelvin. So most important thing for the radiation heat transfer is, first we have to convert all the temperatures in Kelvin if it is available in degrees Celsius. So here it is given in Kelvin, so no problem. Wavelength is given 1.2 micrometer, emissivity that is equals to 0.9, that is given in the data. So now what we have to do, we have to find out our first task, that is monochromatic emissive power at wavelength 1.2 micrometer. So we have to find out what is E lambda B value. And according to the Planck's law, we know that E lambda B, that is C1 lambda power minus 5 divided by exponential function of C2 divided by lambda t into minus 1. So where we have to remember what is the value of C1 and C2. Lambda value is given in the data, t value is also available in the data. So C1 value is given here, that is 3.742 into 10 power 8 watt into micrometer power 4 per meter square, and we have to convert that into watt into meter power 4 divided by meter square. So we will get answer 0.3742 into 10 power minus 15. C2 value is also available with us. So C1, C2, lambda and T, all the things are available here. We have to put all the values here, and based on that we will get the value of E lambda B, that is the monochromatic emissive power. That value is 2.014 into 10 power 12 watt per meter square. So this calculation you have to do, and once you do the calculation you are end up with this answer. This is the first required answer. Now second thing which we have to find out is the wavelength at which the emission is maximum, that is lambda max. So we know that lambda max into T, that is 2898 according to the Wein's displacement law. So we know what is the T value. So the lambda max value is 1.045 micrometer. Now we have to find out what is maximum emissive power. So we have to put this lambda value equals to 1.045 here. So what you can see, E lambda B max, that is 1.285 into 10 power 5 into T power 5 watt per meter square. So we will get the answer, that is 2.01 into 10 power 12 watt per meter square per meter length. So one more answer is available. Now we have to find out what is the total emissive power E. So according to the Kirchhoff law, E, that is equals to EB, that is sigma into T power 4. Sigma value we have to remember, that is 5.67 into 10 power minus 8 watt per meter square Kelvin power 4. Temperature value is known to us. So we will get total emissive power, that is EB, that is equals to 3.352 into 10 power minus 6 watt per meter square. So that answer is also available. And last answer, now we have to consider it as a real surface with emissivity is 0.9. So we have to find out what is E. So in this equation we have to add epsilon part, that is this epsilon we have to add. So what we will get, epsilon, that is 0.9 into 5.67 into 10 power minus 8, and this T temperature is 2773 power 4. So we will get this E value, that is total emissive power of real surface, that is 3.017 into 10 power 6. Definitely this is less than this value, because this is for black body and this is for real surface. So our all 5 answers are available. I hope you are getting this, how to solve the problem, that is also clear to you. Now let us solve one more problem related to the basic laws. So assuming the sun to be a black body having the surface temperature of 5800 Kelvin, calculate first total emissive power, second the wavelength at which maximum spectral emissivity occurs, third the maximum value of E lambda B, fourth the total value of radiant energy emitted by the sun per unit time if its diameter can be assumed to be 1.391 into 10 power 9 meter. So what we have to do is, for the sun the temperature is given and we have to find out 4 answers. So sun temperature is given 5800 Kelvin. Now let us solve it. It is very easy now. temperature is given 5800 Kelvin, diameter of the sun is given 1.391 into 10 power 9 meter. So first part which we have to find out is monochromatic emissive power of the black body, that is sigma into T power 4. Sigma value is known to us, T is known to us, so we will get our first answer, that is 64,200 kilowatt per meter square, or it is 6.42 into 10 power 7 watt per meter square. Second, we have to find out the maximum value of wavelength. We have to find out lambda max. So lambda max into T, that is 2898, or you can say 2.898 into 10 power minus 3. So lambda max is 2898 divided by 5800, that is 5 into 10 power minus 7 meter, that is 0.5 micrometer. 0.5 micrometer. Now we have to find out what is the maximum value of monochromatic emissive power. So it is known to us 1.287 into 10 power minus 5 into T power 5 watt per meter square per meter length, that is meter cube. So we will get the answer 8.45 into 10 power 10 kilowatt per meter square per meter length, or you can say kilowatt per meter cube. Now we have to find out what is the heat liberated, Q. So Q, that is equals to sigma A into T power 4. So sigma value is known to us, diameter value is known to us, temperature value is known to us. So we have to put all the values here. So we will get the amount of radiant energy emitted by the sun, that is equals to 4.38 into 10 power 26 watt. This energy is, you can say, sufficient one to satisfy our daily need of entire earth, or you can say the energy emitted by the sun is more than what is our requirement. Means if we go for solar energy, or if we go for the equipment and instrument which are operated with help of the solar energy, definitely it is a green energy, and definitely we can satisfy all our demands. So friend, we had discussed some numericals related to heat transfer by means of radiation based on the governing laws of heat transfer by means of radiation. So if you like this video, then do not forget to press the like button, share this channel to your friends, and subscribe the channel. So again, this is the QR code of the channel, and my channel name is AVM Tech Android. You can write AVM Tech Android on the YouTube, and you can subscribe this channel, and you can enjoy the free video lectures. Thank you very much.